we're now going to introduce ourselves with nucleophilic aromatic substitution, labeled SNAR. So nucleophilic aromatic substitution, not electrophilic aromatic substitution. Now, let's first start off thinking about nucleophilic substitution of benzenes. And if I were to take benzene and treat it with a nucleophile, I know that there's no reaction that takes place. Likewise, if I were to take an aryl chloride or an aryl halide, so benzene attached to a halogen, and treat this with a nucleophile. We talked about this in the first semester, how aryl chlorides don't typically undergo substitution reactions. And so you see there's no reaction that takes place. However, this isn't always quite true. And when we see that when there's very strong electron withdrawing groups on the benzene ring, those electron withdrawing groups actually activate the ring toward nucleophilic aromatic substitution reactions. In other words, in a nucleophilic substitution reaction, the benzene is the electrophile, and obviously it's reacting with a nucleophile. When we withdraw electron density from the ring, we are actually enhancing its electrophilicity. So we're decreasing its nucleophilicity, and hence toward electrophilic aromatic substitution, they're deactivating, but toward nucleophilic aromatic substitution reactions, they're actually activating toward those types of reactions. So it all has to do with electrophilicity now instead of nucleophilicity. And so we see that here I have dinitrochlorobenzene, right? And when I react this with sodium hydroxide and ammonia, I can actually get substitution of the chlorine for an OH. So it's a substitution reaction, just like an alkyl halide undergoes substitution. Here we have an aryl halide undergoing substitution. Keep in mind, though, you have to have strong electron withdrawing groups on the ring, and they have to be in particular positions, as we're going to see. Now, what is the mechanism of this reaction? Well, we saw with alkyl halides there were two main mechanisms: SN1 substitution, SN2 substitution. Well, this can't be an SN1 substitution. Why? If I look at that ring and I see that all those pi, the p orbitals around that ring, delocalizing that charge, what happens in an SN1 reaction? The leaving group comes off, right? So that's the first step. So what do I generate when the leaving group comes off? I generate a carbocation. So now I have this carbocation. But if I look closely at it, when the carbon is sp3 hybridized and a leaving group comes off, it generates a carbocation that's sp2 hybridized. When an sp2 hybridized carbon generates a carbocation, what is the hybridization of that carbocation? Well, it has to be sp hybridized. And if it's sp hybridized, that means that carbon has to be planar. And there's going to be a huge activation energy barrier to overcome that, the formation of that intermediate. And so we know that the leaving group isn't going to just come off and generate a carbocation. Now, what about SN2? Well, it can't be SN2 either. Remember, again, drawing our benzene ring with our possible leaving group, in an SN2 reaction, what happens? The nucleophile attacks the carbon with the leaving group. And it attacks the sigma star antibonding orbital of the carbon, right? Well, where is that sigma star antibonding orbital located? It's actually located right in the middle of the ring. And there is no way that the nucleophile can actually get to that carbon. And so this reaction doesn't take place. backside attack is impossible. All right, the other puzzle is that the NO2 group, or the electron withdrawing group, and it has to be a strong electron withdrawing group, typically it's NO2, and that NO2 group has to be ortho or para to the halogen that's coming off, right? So notice in the above example, I have a nitro group that's ortho to the chlorine, and I also have a nitro group that is para to the chlorine. Why is this? Well, let's think about what's happening in this reaction. We see that if I'm treating paranitrochlorobenzene with methoxide, we know methoxide is a good nucleophile, right? We've seen this as a nucleophile before, and it can attack the carbon with the halogen, right? So what happens after that? Well, it must be that obviously we have to break a bond. And the chlorine bond isn't going to break, we saw, based on orientation of orbitals. And so what has to happen? Well, a pair of electrons from the benzene ring has to go onto an adjacent carbon. And we generate this carb anion, right? So the NO2 group's on the ring, and I'm generating a carb anion. And of course, that carbanion can be stabilized through resonance, right? I can donate it into the ring and take another pair of pi electrons and donate them onto that carbon. I now create another carbanion, and of course, I can go through the ring and generate another resonance structure where the pair of electrons are now on the other ortho position relative to that chlorine and the OCH3 group, right? So here I have my three resonance structures, but notice, and this is why the NO2 group has to be in the ortho position and the para position. So here it's in the para position, and I can take that pair of electrons and I can draw another resonance structure. And when I do so, and I donate those pair of electrons onto the nitrogen, a pair of pi electrons from the NO swing up to the oxygen. And so here I generate a fourth resonance structure to stabilize it. And this resonance structure is called the Messenheimer complex. And it's named after a woman actually that came up with this particular mechanism. So this Messenheimer complex stabilizes it toward nucleophilic aromatic substitution. And that's why the NO2 group has to be on the ring. So number one, it's withdrawing electron density, but number two, once the nucleophile actually attaches to the ring, it helps to stabilize the intermediate. Now, we're talking about a substitution. How does the chlorine come off? Well, we can think about a series of steps that will eliminate that chlorine. So one of the oxygens, doesn't matter which one, donates a pair of electrons back to the nitrogen. The nitrogen-carbon bond, now pi bond, can donate a pair of electrons to the ring, and we can then donate a pair of electrons from that pi bond on the left back to that carbon, and now a bond has to break. And of course it could be the OCH3 group, which we would get starting material back again, or it could be the halogen. And the halogen's a much better leaving group than the OCH3 group, and certainly this is going to drive the reaction, and we get substitution occurring. Notice when the NO2 group is in the meta position, you can't form the Messenheimer complex, and so substitution will not occur. So if I had meta-nitrochlorobenzene and I tried to treat it with sodium hydroxide or sodium methoxide, I would get no reaction to occur. The nitro group has to be para or ortho to the halogen. All right, so now that we've seen nucleophilic aromatic substitution reactions of benzene derivatives, what happens with heterobenzenes? And we can start with pyridine. We see that pyridine's actually less stabilized aromatically than benzene is. And so it's actually more prone to accepting nucleophiles. So the nitrogen on the ring can actually accept a pair of electrons. We're going to see that how that plays out. Here we have pyridine reacting with a nucleophile. So again, notice I want you to think about parallels. Benzene never reacts with a nucleophile. Only aryl benzene, aryl halide, so benzene with a halogen, and only when there's strong electron withdrawing groups on it. But pyridine can actually react by itself with a nucleophile. And what happens is that nucleophile tends to attack a carbon adjacent to the nitrogen. And we can draw resonance structures where, again, we're putting a negative charge onto the ring. So I'm generating a carbanion where the nucleophile has now added to that 2 position. And of course, I can draw resonance structures, donating that pair of electrons back into the ring, and pi electrons swing up to the carbon on the left. So here's my resonance structure. And then, of course, another resonance structure where I'm donating those electrons from the anion into the ring, and I'm taking the pair of electrons from that pi bond and actually putting it onto the nitrogen itself. And so I get this resonance structure where the nitrogen has accepted a pair of electrons. It is now an anion. We know that this is going to be the highest contributing resonance structure because nitrogen is more electronegative than carbon is, and so this is the preferred Lewis structure, right? So this is the major resonance contributor. All right, so what happens now? Well, if we think about what's taking place in terms of substitution, I have to lose that hydrogen. And I'm going to do so simply by taking, again, this intermediate has lost its aromaticity. And there's a driving force to regain its aromaticity. How is it going to do that? If it donates a pair of electrons from the nitrogen back onto the ring, now I have to break that carbon-hydrogen bond. To do so, I have to lose a hydride, right? So I have to lose the hydrogen and its electrons. So this is what happens. And this is very unique for pyridine. We typically don't see a loss of hydride. Hydride is not typically a good leaving group, right? But again, that driving force for aromaticity, right? The stability of the aromaticity is going to render that hydride an okay leaving group in this particular circumstance. So now I have my substituted pyridine plus hydride. And we see this in a particular reaction called the Chichi-Bobbin reaction. The Chichi-Bobbin reaction. I just love saying that. The Chichi-Bobbin reaction is where you take pyridine and you react it with potassium amide in ammonia, followed by an aqueous workup. What happens? The nucleophile in this case is the amide anion, and it adds to the pyridine ring. And if we think about the mechanism of this reaction, we have pyridine reacting with the amide, NH2 minus, and we get donating of electrons from the NH2 onto that carbon. And I'm simply going to, show the electrons going onto the nitrogen. I mean, we can show the resonance structures. If I asked you to draw the resonance structures, you should be able to do so. But in essence, I'm going to draw one of the resonance structures because we know this is the most stable resonance structure where the nitrogen has that negative charge. And I form this intermediate, right? Now, this intermediate, the pair of electrons from nitrogen is then going to go back into the ring, and we're going to lose a hydride. And so we get this. Okay, so this looks like it's our product, and it certainly is our product. But under the conditions, hydride is a very strong base, and we have an amine that is, slightly acidic. And so we can get a deprotonation of the amine, right? And we generate an amide ion plus hydrogen gas, right? So hydrogen is produced in this particular reaction. And now we have our amide anion, which we don't want. We want the amine. So how do we go about getting the amine? Well, in a second subsequent step. So notice, these are different steps. I can't add water directly to this reaction. I have to wait for my product to form, be deprotonated to form the amide anion. Then I can add water to this, and I can get the amide protonated. And that leaves me with 2-aminopyridine. Of course, I also am generating hydroxide in this case as well. Another reaction, nucleophilic substitution reaction of pyridine, involves organolithium reagents, right? So here I take an organolithium, and if you recall back from the first semester, organolithiums are like, carbanion-like. And so that anion, the nucleophile, is the R group, right? And of course I'm generating lithium hydride as well. And lithium hydride can then be treated with water. And then I get my alkylated pyridine plus lithium hydroxide, and then I generate hydrogen gas again. So as an example, I take pyridine, I treat it with propyl lithium, or I could use all sorts of organolithiums: butyllithium, propyllithium, pentalithium, in THF, a subsequent aqueous workup. So again, 2 steps, right? Very important to understand 2 steps. React with organolithium in dry conditions, THF as a solvent, followed by a subsequent aqueous workup. And I get, in this case, propyl, so 2-propyl pyridine, and I would generate lithium hydroxide and hydrogen in the process. Now we can also convert pyridine bearing a leaving group at the 2 or 4 position into other substituted pyridine derivatives, right? So we saw that benzene doesn't undergo nucleophilic substitution reactions, but pyridine itself does. We did see that benzene, in select cases with a halogen on it and electron withdrawing groups, will undergo substitution. Well, the same holds true with pyridine, and these are called ipso attacks. So when pyridine has a halogen or a leaving group on it, we can get substitution of that leaving group. So for example, here I have 4-chloropyridine, and if I react 4-chloropyridine with sodium methoxide in methanol, the methoxide is my nucleophile, and so I can substitute the chlorine for a methoxy group. All right, so the mechanism of this reaction is going to be similar to what we saw before. The pair of electrons on the methoxy group are going to attack the carbon bearing the leaving group, right, in this case chlorine. And we're going to then place electrons onto the ring. I'm going to draw you one resonance structure where the pair of electrons is on the nitrogen. Why? Again, because we know that this is going to be the major resonance contributor. So here I have the nitrogen anion, and now I have to kick off that halogen. How am I going to do so? Well, the nitrogen is going to donate a pair of electrons into the ring. The electrons from that pi bond are going to move up to create a new pi bond, and now the halogen can leave. Again, because it's a better leaving group than the OCH3 group. And I generate my product plus chloride.